Hi everybody, welcome to another video in Calculus 1, section 7.3, logarithmic and exponential function with all the bases. So on previous section we have the natural log and the natural exponential function, derivative and integral of the calculus of those functions. Now we focus on the exponential function in general. So b could be anything. The base is not equal to 0. The base is not equal to 1 and greater than 0. Because if the base is 1, 1 raised to any power is still 1. Right? So in that case, it's just a constant. And it's not really interesting in that case. Right? Properties of exponential function, the domain and range. And the graph will go to the point 0 and 1. And the line y equal to 0 is the horizontal asymptote. So we have those exponential function. If the base is positive, if the base is greater than 1, it is increasing. If the base is between 0 and 1, it is decreasing. So all of that is just the algebra of exponential function. The logarithmic function and exponential function are symmetric on the line y equal to x because they are inverse of each other. And the properties of inverse function, b to log base b of x is equal to x, and log base b of b to the x is equal to x as well. Right, so we have that. Now the calculus part of it. What is the derivative and the integral of exponential function in general? Well, if b is greater than 0, then the derivative of b to the x is equal to ln of b to the x of the x's. So how do we get that? Well, let's say if we have y equal to b to the x in general. Now we have to make some trickery here. Remember, we can only take the integral if it is e or ln, right? We can only find derivative if it is b e to the x. This is b to the x, so it's not quite the same. So we have to rewrite this as something that we can find derivative of. So how about e and then ln of b to the x? Because when we write like that, e and ln cancel out, we have b to the x, right? Because we can take that derivative, right? Now, just the ln part, we can take the x on the outside, and that gives us e x ln of b, or we just say e ln of b, which is a constant, times x. Then we take derivative. And the exponential rule, e to the same thing, derivative of the exponent. So ln of b times x and ln of b times x. Derivative of that is just ln of b, and this is the same as b to the x, because all of that equal to each other, b to the x. And then the derivative of this is just ln of b. So that's exactly what we have. So pretty much we're going to have the same exponent, but we just times ln of b. Now this is consistent to the case where we have e to the x. If we use this rule, we will have ln of the base and the same exponent, the same power term. ln of a is equal to 1. So that's why this is just e to the x. That's a special case. If any other bases, we're going to time ln of the base times that exponent. So that's simple enough, right? Right. Now I have 2 to the x, which is exponential rule, derivative very straightforward. This is some other base than e, right? So we have the ln of 2, which is the ln of the base, and then the same thing, 2 to the x. And that's all we do, really. So when we have other bases than e, just copy that the same and then multiply by ln of the base. And that's pretty much it. Now this, if we rewrite this as 12 times 3, the power is t over 12. Or if I write that, it will be 1 over 12 times t. And 1 over 12 times t is the exponent. So when we take derivative, the 12 is a constant, will stay there. Now, 3 to the that is going to be ln of the base, and then the same thing. Just that chain rule, we have to take derivative of the parentheses there. So we have 12 ln of 3, and then 3, 1 over 12 t. Derivative of that is just 1 over 12. 12 on the top, the 12 at the bottom cancel out, and we left just ln of 3 and 3 times 3 to the power of 1 over 12t, or we just write t over 12. Right, so yeah, so if we have all the base on x, all the base on e, we have to write ln of the base first, and then just copy what we have there. Same thing here. Different here is that we have the chain rule. Alright, so that is the derivative. Now the integral instead of multiplying by the base, we divide by the ln of the base, because the integral is the antiderivative plus c, right? If the derivative is multiplying, antiderivative will be divided, because those tend to be different than the other. I mean, by different than the opposite way of the other. One is multiply, one is divide. It's just like in the power rule. One will multiply in derivative and divide in the integral. Right. So just divide by the base and copy the same thing. So here, integral of 2 to the x, well, the base is 2. So 1 over ln of the base, and then 2 to the x, same thing. X squared though is the power rule, x cubed over 3 plus c. And essentially that's all we have. Yeah, okay, just stop like that. Right. So something to the x power, first divide 1 over the base, ln of the base, and then copy that term. Right. Now let's something else. We have this. Now we have 5x times 3 to the negative 2x squared plus 1. The negative 2x squared plus 1 is on the exponent. So in that case, let's do substitution on the exponent to be u. And we take the derivative. Negative 4x. Move the dx. And divide by the negative 4x. 5x still there, and then 3, the negative 2x squared plus 1 is u, dx is du over negative 4x. X and x cancel out. Negative 4 will stay at the bottom. The 5 will stay on the top. What's left though? It's just an exponential function. So it's easy, very convenient to do that. Yeah, because substitution, it has to work if all the x's cancel out. We have everything in terms of u, and that's exactly what we have, right? So this is negative 5 over 4 integral of that. First thing we divide by the ln of the base, and we copy the same thing. So we have negative 5 for ln of 3 times 3. U is negative 2x squared plus 1 plus c. So yeah, that's what we have. Right. Now this, what do we let equal to u? Well, we can let u equal to square root of x at the bottom. But if that is the case, 6 to the power of negative x square root of x, that's complicated. So we might want to let u equal to the exponential on the top. Right. So if we want to make things, nah, this is fine. That's fine. Just go ahead and do it. U equal to negative square root of x. And of course, when we do that, it will be easier to take the derivative if we write that as x to the 1/2, which is equivalent to square root. Now we take the derivative. Negative 1/2 x to negative 1/2. Right, we try to get the x by itself. So move the dx over. Right, now just divide this at the bottom, but it will be easier if we multiply by negative 2 first. So in that case we don't have the negative and the 2 at the bottom, so that gives us negative 2 du equal to x to the 1/2, x negative 1/2 dx. Now we can divide the x to negative 1/2 to the other side. And negative exponent move to the top. We have negative 2 x to the 1/2 du is equal to dx. Right, let's change the limit as well. U equal to negative square root of x. When x equal to 1, we have negative 1. When x equal to 4, negative 2. So instead we go from 1 to 4. Right, ready for substitution. We go from 1 to 4, but x equal to 1, u equal to negative 1. When x equal to 4, u is equal to negative 2. right? That's better. Now substitution. 6 to the u over square root of x. The x is that it's not subtract. It is multiplied to it. Now, the x square root of x at x to the 1/2, that's actually the same thing, right? So we can cancel out -2 here, bring it outside. And the integral from -1 to -2 of 6. Yeah, everything cancel out or bring out of the integral. We have 6 to the u du. By the way, what we see here is -1 and -2. Actually, -1 is bigger than -2. So when the integral, we want to go from the smaller number to the bigger number. So we use these properties. If we interchange the limit, we change the sign. So there's a negative here. I will interchange the limit. So that will be just 2, but the integral will go from -2 to -1. And then 6 to the u du. Of course, u go from -2 to -1. And integral of 6 to the u is 1 over ln of the base. And then the same thing. Going from -2 to -1. Notice that the 6 to the u, I do not multiply the 2 into the 6. Because 6 is the base. We cannot just take something and mess with the base. But we can just have 2 ln of 6. 6 to the u, going from -2 to -1. And that gives us 2 ln of 6 times 6 to the -1. Subtract 2 ln of 6. 6 to -2. If we want to, we can factor out the 2 over ln of 6. 6 minus 1 to -1 by 6 to -2. Now let's check, because usually when we get the definite integral, we should check the answer. I recommend that you do. 6 to the power of negative square root of x over square root of x dx. That's what we have. Is that the same thing as this? 2 divided by ln of 6 times 6 to the -1 by 6 to the -2. Yeah. So, yes, so when we have the square root, or that's the same as the 1/2, so just make sure whatever we let u equal to, it should cancel with the rest of the problem. So we let u equal to square root of x, which will cancel with square root of x. So that works out perfectly there. Right, that's what we have for this problem. Now we go to the general logarithmic function. So now, derivative of the log base b of x. Now if we have different base than e, we have once again divide by ln of the base. Right. So derivative should be simple though. Just use that formula. Derivative of the log is the reciprocal function times ln of the base, which is 5. and then derivative of the parentheses. Just happen that we have 2x plus 1 there. So we have 1 over 2x plus 1 ln of 5, and then derivative of 2x plus 1 is 2, and we just put the 2 on the top. Do not cancel with the 2 at the bottom because there's a plus 1 here. So that is that pretty much, right? So just the reciprocal function, but have to multiply by the ln of the base. Right. Next, we have a product rule here: u equal to x, v equal to log base 2 of x. Take derivative of log base 2 of x is 1 over x times the ln of the base. Right? So, yeah, just a rule. And now we integrate. The product rule. U prime v plus u times v prime an x on the top and x at the bottom cancel out. So that's why we have log base 2 of x plus 1 over ln of 2. Right, now I just want to go back and prove this because this is very easy to prove. Now if we have the function is any base older than e, it still can be e. We used what we call the chain of bases formula. That will be ln of x over ln of b. Sorry, you don't see that. Yeah. So if we write log base b of x as ln of x over ln of b, or we just say 1 over ln of b times ln of x, and then we just differentiate derivative. We have the constant here. Derivative of ln of x is 1 over x, and so that just gives us 1 over x ln of the base. So if we want to, of course, we can just rewrite log of different base using the chain of bases formula, which is this one. And that is the proof. Very simple, right? So if we have all the bases, then e, of course, if we use base e, ln of e is 1, so it still work. That's fine. So derivative of exponential function. Okay. Derivative we multiply by the base. Integral of exponential function we divide by the base. What we see here is, notice that rather than we have derivative and integral, we do not have the integral of the exponential, do not have the integral of the ln of x. So that's what brings up to the next page. So what is integral ln of x? So we do not have this in calculus 1. We will study this in calc 2. However, we luck our way into the answer, I think. Remember, we have this on the previous section, where we're trying to find the derivative of x times ln of x, right? The derivative of that is ln of x plus 1. So let's just write out. We have x ln of x. We took the derivative, and that gives us ln of x plus 1. Yeah, so that's what we have from the previous section. So how did that help? Well, we can integrate both sides, right? Integrate that side. Integral and derivative pretty much cancel out, so we just have x ln of x, and then we can split this dx plus integral of dx, which is x. So x ln x, yeah, we can do the plus c here, plus constant, which I forgot. And then we have integral of ln of x dx, and then plus x. So if I move the x over, I do have the integral of ln of x dx is equal to x ln of x minus x plus c. So we luck our way into it because we found the derivative would turn out to be something nice like this, and integrate both sides, integral and derivative cancel out. Not really cancel out, but when it cancel out, we still have a constant c there. Yeah, but that is one way to do it. Of course, in the calculus 2, there's a more general way, a more direct way. But this is more like luck, which should actually get to something that we can solve for the integral. Right, because when we plus the constant c, we can just put the c on either side. Right, that's good there. Now, here I just want to summarize everything. We have derivative and integral. So let's just fold the page in half. So now, here's all the rules we have. And a little more general. Right, so let's say derivative, integral. Of course, you will have this already in the final exam folder, I think. Right, first power rule, derivative of x to the n is n x to n minus 1. So derivative, we multiply the integral, we divide. That works, but notice that the base, the n cannot be negative 1. Otherwise, we divide by 0. When it is divided by 0, when n equal to negative 1, we have just 1 over x. That is ln of absolute of x plus c. And of course, we have derivative of constant equal to 0. Okay, of course, the integral of the constant is kx plus c. Right. So that is the the power rule. Next, let's go over all the trigonometry. Right, I'm going to do which one adjustment here. Derivative of sine x is cosine x, right? Now, something more general. What if we have a constant k x? Take derivative of that. All we need to do is just use quickly sine of kx derivative is equal to cosine of that derivative of the parentheses, right? Will be just k. So when we have either x, if there's a k, that's perfectly fine. We just multiply to it. And then sine is cosine. Cosine, if there's a k, then we just, I should put the parentheses here, do I? It's going to be k sine of kx. Of course, it's negative. Derivative cosine negative sine. All we need to do is just multiply the k to it. Now to get the idea, tangent, now I just write like this, is secant square, but then we multiply to it. Cotangent negative k cosecant square secant is k secant tangent and then cosecant negative cosecant cotangent. Right, of course you can check the antiderivative and go back here to there, but that's certainly we do. But I will not write all of them. You get the idea. Now we do integral of cosine of kx. Integral of cosine is sine, but if the derivative is multiplying, all of them multiply by k, right? Here we just divide by k. Yeah, or we use substitution. We don't need to. It's better if this is just kx. By the way, if this is sine of kx plus 2, do not do this. It's only work if it is a constant times x. And so derivative is multiply, integral is divide. Integral of sine of kx. Integral of sine is negative sine. But once again, we divide by the coefficient of x, and that gives us cosine of kx. And then all of all the rules. Right, what do we have for tangent? It is ln of secant, right? You know, ln of secant, yeah. And then we divide by k. In the previous section, that's what we have. and then cotangent kx dx. Again, we just divide by k, and then cotangent. I'm not sure why I have an s here for no reason. Just ln of sine kx plus c, and then secant and cosecant, same thing. We just need to divide by k. Just go from the previous section, and instead of x we have kx, we just substitute kx there and then divide by k. Of course, I'm not right. We should have the secant square x dx is equal to tangent too, but I'm not going to write those integral. If we have the k here, just simply divide by k. So yeah, I'm not writing those out. Now the exponential function. Yeah. Remember, we still have this. Let's just say and then secant tangent is 1 over k secant. Yeah, but I'm not going to write those here. Right, exponential function. E to the x is still e to the x, but now let's put a k there. Derivative, we just multiply by that constant. In integral, we will divide. Right, if we have some other bases, here we just need to multiply by the base, and then the same thing. Right? Except that k, so we multiply k, and then same thing here. So first we divide by k, and integral will be the same thing, but we have to divide by the basis. So integral of exponential function just divide by the base. Here we multiply by the base, integral we divide by the base. Yeah, so multiply by k ln b, divide by k ln b, same thing. Yeah, finally, logarithmic function. Now, log is the exception. We do not have integral for the log, at least that. Ln of kx. This is just 1 over x, etc. What happened with the k, right? Yeah, what happened with the k. So this is exception. All of this, where we have, instead of x, we have kx. We just multiply all the constant k, and the integral we divide by the constant k. Or except for that one, but that is just a constant. Now, if we have the, because this is constant of x, so that's different. We divide all by the constant. But here, remember, if we have ln of kx, we can write that as ln of k plus ln of x, derivative of it. Derivative of constant is 0, derivative of ln of x is 1 over x. So even though there's a k here, it doesn't matter. The derivative is just 1 over x. That's a special case. Of course, then we have the same thing. Log base b of kx will be same thing as log base b of k and log base b of x. So the k here doesn't really matter. We just have 1 over x and divide by the base. Yeah, that's what we have. Right, so that's pretty much the derivative and the integral. Of course, I'm not writing this here, but it will be in here as well. So derivative and the integral, when we multiply by k into x, just kx. If it is kx plus something else, it doesn't work. It has to be a constant times x. If that is the case, derivative we just multiply by the constant. Integral we divide by the constant. So we have the power rule, trigonometric function, exponential function, logarithmic function. Those are the functions we have for derivative. Integral, pretty much we have all three, except we don't have the integral for the log. This is in calculus 2. Yeah, just want to quickly put down everything that we have. Of course, there's a much nicer formula we have online in my note. But other than that, that's what I want to cover for calculus 1. As always, thank you for watching.